Welcome. Aware, Doombella, Doomalime, Molo, Sobona, Hukundat, and a warm welcome to the Adulo Knowledge Cast, the podcast where your curiosity meets insightful conversations. Today, we're going to be tackling a topic that sounds a little intimidating at first. Partial Differential Equations, or PDEs for short. But trust me, we're going to make this as lekker and easy to understand as a Sunday afternoon braai.
That's right. We're going to break down the complexity of PDEs, relate them to everyday South African life, and even delve into the fascinating history behind these mathematical marvels.
We're diving deep into a textbook excerpt called Introduction to Partial Differential Equations.
Too.
Now I know what you're thinking. Textbook-ish. But don't worry, this isn't about memorizing formulas. It's about unlocking the secrets behind those formulas and seeing how they apply to the world around us. Imagine trying to figure out how heat spreads through a pachi pot, or how the wind creates waves on a dam. Those are PDEs in action.
Exactly. PDEs describe how things change over both space and time, involving multiple variables. Think about the temperature of your Bray grid. It changes not just over time as the coals heat it up, but also across different points on the grid itself. That's where PDEs come in. They help us model and understand these dynamic processes.
So these equations are like a secret code to understanding how the universe works.
In a way, yes. The book we're looking at focuses on three particularly important PDEs: the wave equation, the heat equation, and the Laplace equation. Think of them as the big three, the Amapiano hits of the PDE world.
How do those names sound familiar? I vaguely remember hearing about them back in my school days, but I can't say I understood much about them back then.
Well, that's what we're here for. We're going to demystify these equations and show you how they underpin many phenomena we encounter every day.
Before we get into the specifics of each equation, I'm curious about something. Are all PDEs created equal? Or are some, let's say, a bit more challenging to work with than others?
That's a great question. And it leads us to the concept of linearity. You see, PDEs can be linear or nonlinear. To understand this, think about making chakalaka. A linear recipe is one where you can double the ingredients and still get chakalaka, just twice as much. But a nonlinear recipe is like a carefully balanced shisanyama marinade. Changing the quantities even slightly can completely alter the final taste.
So a linear PDE is predictable and straightforward, like your favorite bunny chow spot that always delivers the goods, while a nonlinear one is more like an experimental pachi recipe, could be amazing, could be a total flop.
A perfect analogy. This distinction is crucial because linear problems are generally easier to solve. We can often apply something called the superposition principle, which means breaking down a complex problem into smaller, simpler parts, solving those individually, and then adding the solutions back together like building blocks to get the full picture.
So it's like assembling a braai stand. You start with individual pieces and end up with something sturdy and functional. But what about those nonlinear equations? Are they a complete mathematical morass to deal with?
They can be tricky, but that's where things get really interesting. Nonlinear PDEs often describe more complex and nuanced phenomena in the real world. Think about the unpredictable flow of traffic in Johannesburg, or the way weather patterns develop. These are situations where nonlinear equations reign supreme.
Okay, so linearity versus nonlinearity is a key concept when it comes to PDEs. But I'm guessing there are even more ways to classify these mathematical beasts.
You're right. When it comes to second-order linear equations, those involving second derivatives, we can further classify them into three main types: elliptic, parabolic, and hyperbolic. Each type has unique characteristics and describes different kinds of phenomena.
Okay, I'm intrigued. But before you unleash a torrent of technical jargon, can you give me some real-world examples for each of these types? Something a true South African can relate to.
Absolutely. Imagine you've got your Bray grid nicely heated up, the steady state temperature distribution on that grid, after it's been going for a while and the heat has spread evenly, can be modeled by an elliptic equation. It's all about equilibrium, a state of balance.
So it's like that perfect moment when the borers is cooked to perfection and the grid is radiating a consistent heat.
Precisely. Now think about how the heat actually spreads through the grid over time. That's a classic example of a parabolic equation in action. It describes those evolving processes where things change gradually, like heat diffusing through a material.
All right, so elliptic is about a steady state, and parabolic is about those gradual changes over time. What about hyperbolic equations? What kind of South African scenario can you conjure up for that?
For hyperbolic, let's turn up the volume. Imagine the vibrations of a drum head or the sound waves traveling through a vuvuzela at a soccer match. Those wave-like phenomena, those oscillations that travel and spread out, are governed by hyperbolic equations.
Now that's a vibe I can get behind.
Yeah.
So these classifications help us understand what kind of behavior to expect from the equation even before we try to solve it, right? It's like knowing whether you're in for a smooth ride on a tar road or a bumpy journey on a gravel path.
Exactly. It gives us a roadmap for approaching the problem and helps us choose the right tools for the job.
Okay, so we've laid the groundwork and explored some key concepts related to PDEs, but I'm eager to dive deeper into each of those big three equations you mentioned earlier. First up, let's talk about the wave equation. I'm ready to ride those mathematical waves.
Let's do it. We're going to unpack how the wave equation describes everything from the music we hear to the ripples in our morning coffee.
Sounds good to me. But before we get carried away with all the excitement, I think it's time for a quick tea break. We'll be back shortly to delve into the world of the wave equation.
All right, let's get back to our deep dive into this fascinating world of PDEs. Remember those big three equations we mentioned? Well, we're about to tackle the first one, the wave equation.
I'm all ears. Every time I hear music or see ripples in my coffee, I'm going to be thinking about this wave equation now. So, tell me, who was the clever oak who first figured this whole thing out?
That would be Jean-Baptiste Laurent D'Alembert, a French mathematician from the 18th century. He made groundbreaking contributions to the field of PDEs, particularly with his work on the wave equation.
D'Alembert. That name rings a bell, but I can't say I remember much about him from my school days.
Well, you should. He developed an explicit solution for the one-dimensional wave equation, which is a pretty significant achievement. Essentially, it means we can use his formula to predict exactly how a wave will behave over time.
Okay, I'm no maths whiz, but explicit solution sounds impressive. So if we know the initial conditions of a wave, like how a guitar string is plucked, we can use D'Alembert's formula to calculate its position at any point in time.
Exactly. It's like having a mathematical crystal ball for waves. His solution involves something called characteristics, which are like special paths in space-time that tell us how the wave propagates.
So characteristics are like the GPS for waves, guiding them on their journey.
That's a great way to think about it. Imagine you drop a pebble into a still pond. The ripples spread outwards in circles, right? Well, those expanding circles represent the characteristics of the wave equation, showing us how the disturbance propagates over time.
Okay, I'm starting to see the picture. Now I remember hearing about another concept related to waves, something called Huygens principle. Does that ring a bell?
Absolutely. Huygens principle is a powerful idea that complements D'Alembert's work. It states that every point on a wavefront can be considered as a new source of secondary wavelets, and these wavelets combine to form the next wavefront.
Hold on, let me try to wrap my head around this. So it's like each point on the wave is a mini wave maker, sending out its own little ripples, and all those mini waves join forces to create the overall wave we see.
Precisely. It's like a synchronized dance of mini waves, each contributing to the overall motion.
That's incredible. It's amazing how something so complex can be broken down into these smaller, simpler elements.
That's the beauty of mathematics. It helps us understand the underlying order and patterns in the universe, even in seemingly chaotic phenomena like waves.
So we've got D'Alembert's solution, which is like a recipe for predicting wave behavior, and Huygens' principle, which shows how waves propagate through this intricate dance of mini waves. I'm guessing the wave equation isn't just about ripples and ponds, though, right?
Of course not. It has wide-ranging applications in fields like acoustics, electromagnetism, and even quantum mechanics. For instance, the sound waves traveling through a vuvuzela at a soccer match can be modeled using the wave equation.
So every time I hear that iconic vuvuzela blast, I should be thinking about D'Alembert and his wave equation.
Exactly. And it's not just about sound. The vibrations of a bridge as cars drive over it, the seismic waves generated by earthquakes, and even the behavior of light, all of these phenomena can be described using the wave equation.
Wow, I'm starting to see the wave equation everywhere now. It's like a hidden code underlying so many aspects of our world. But before we get too carried away with the wave equation, we've got another important PDE to explore, the heat equation.
All right, let's shift gears and delve into the world of heat flow and diffusion. Get ready to feel that mathematical heat.
I'm already feeling warmer just thinking about it. Let's fire up those bright coals and tackle the heat equation. All right, we've explored the wave equation and all its fascinating applications, from music to those iconic vuvuzela blasts. Now it's time to turn up the heat, both literally and figuratively, as we delve into the heat equation.
That's right. The heat equation, just like the wave equation, describes how things change over time. But in this case, it's all about how heat spreads or diffuses through a material.
So imagine we've got our bright coals burning bright. The heat equation can help us understand how that heat gradually travels from the fiery coals to the borers sizzling on the grid.
Exactly. Think about how those coals heat up the grid. Initially, the area closest to the coals gets hot, but as time goes on, the heat spreads outwards, eventually reaching the edges of the grid and even the air around it. That's the heat equation in action, describing that gradual diffusion of heat.
Okay, that makes sense. But I remember reading somewhere that the heat equation has some surprising connections to other seemingly unrelated phenomena. Is that true?
Absolutely. One fascinating link is to something called Brownian motion, named after the botanist Robert Brown who first observed it. You know how sometimes you see those tiny dust particles dancing in a beam of sunlight?
Yeah, it's like they have a mind of their own, jiggling around in all directions.
Exactly. That seemingly random movement of particles suspended in a fluid is Brownian motion. And what's remarkable is that Albert Einstein, yes, that Einstein, connected this random motion to the heat equation.
No ways. So the same equation that describes how heat spreads through my bride grid also explains those tiny dust particles dancing in the sunlight.
You got it. It might seem strange at first, but both phenomena are driven by the same underlying principle: diffusion. Whether it's heat energy spreading through a material or particles randomly bouncing off each other in a fluid, the heat equation provides a mathematical framework for understanding how things spread out over time.
That's mind-blowing. Einstein truly was a genius to see that connection. So the heat equation isn't just about brides and warm, fuzzy feelings. It's got a much broader reach.
Definitely. It has applications in diverse fields like physics, chemistry, engineering, and even finance. For instance, it's used to model how pollutants disperse in the atmosphere, how heat spreads through a computer chip, and even how stock prices fluctuate over time.
Wow. The more we delve into these PDEs, the more I realize how much they underpin our understanding of the world around us. But there's one more concept related to the heat equation that I'm particularly curious about. Something called infinite propagation speed. No, that sounds like something out of a sci-fi movie.
It might sound strange, but it's a fascinating aspect of the heat equation. Imagine you drop a tiny drop of food coloring into a swimming pool. According to the heat equation, even though it takes time for the color to visibly spread throughout the entire pool, in theory, even the farthest corner of the pool will be affected instantaneously, even if it's kilometers away.
Wait, hold on. Are you saying that the color travels at infinite speed? That doesn't seem physically possible.
It's important to note that this infinite propagation speed is a theoretical concept, not something we observe in reality. In practice, it takes time for the color to diffuse and become noticeable throughout the pool. But the heat equation highlights the idea that even tiny disturbances can have far-reaching effects, even if those effects are initially very small.
Okay, that makes a bit more sense, like a ripple effect. But instead of water waves, we're talking about the diffusion of heat, or in this case, food coloring. So in theory, a single drop of food coloring could eventually affect the entire ocean.
Theoretically, yes, although realistically, factors like currents and mixing would play a significant role, and it would take an incredibly long time for that single drop to have a noticeable impact on such a vast body of water.
That's incredible to think about. It shows the power of the heat equation to describe diffusion on a massive scale.
Absolutely. It highlights the importance of considering even small-scale phenomena and their potential for wider impact.
Well, we've covered a lot of ground today, from the wave equation to the heat equation, from vibrating drumheads to those mysteriously dancing dust particles. I must say I'm feeling a bit overwhelmed, but in a good way. It's amazing to see how these mathematical equations connect seemingly unrelated phenomena and reveal the underlying patterns of the universe.
I agree. It's been a fascinating journey exploring the power and beauty of PDEs, and we've only just scratched the surface.
I know. I'm already eager to dive deeper and explore more of those hidden mathematical wonders. But for now, I think it's time to let our brains cool down a bit. Thanks for joining us on this deep dive into the world of PDEs.
It's been a pleasure. Hopefully you now have a newfound appreciation for the elegance and far-reaching impact of these mathematical marvels.
And remember, folks, the next time you braai, listen to music, or simply watch those dust motes dancing in the sunlight, take a moment to appreciate the unseen mathematical forces at play. Stay curious, South Africa. Until next time, sharp, sharp.